A random forest builds many trees in parallel and averages them. Gradient boosting takes the opposite approach. It builds trees one at a time in sequence, where each new tree is dedicated to fixing the mistakes of all the trees before it. It sounds simple, and it is, and it's the algorithm that wins more tabular competitions than anything else. Here's the core contrast. A forest grows its trees independently and lets them vote, wisdom of an independent crowd. Boosting grows its trees in a line, each one looking at where the team is still wrong and trying to patch exactly that. Not a crowd of equals, a relay where each runner cleans up after the last. Boosting starts almost embarrassingly with a terrible model. For predicting a number, the first guess might just be the average of everything, a flat line that's wrong almost everywhere. That's fine. The whole method is built around steadily shrinking how wrong it is, one small correction at a time. For every data point, look at the gap between the current prediction and the truth. Those gaps are the residuals, the errors still left over. They're a map of exactly where the model is failing and by how much. Boosting's next move is to study that map and attack the biggest mistakes directly. Here's the twist that makes it work. The next tree isn't trained to predict the original target. It's trained to predict the residuals, the errors themselves. It learns the pattern in what we got wrong. Wherever the model was too low, this tree says add a bit. Wherever too high, subtract a bit. Then we add that correction tree to our running prediction, but only a small fraction of it, scaled down by a learning rate. Small, cautious steps add the error correcting tree. The predictions improve a little, and a new smaller set of residuals appears. We don't fix everything at once, we nudge. Now just repeat. Compute the new residuals, fit another small tree to them, add it in, scale down. Round after round, hundreds of times, each tree shaving off a little more error. The crude flat line slowly bends into a precise fit. The ensemble is the sum of all those tiny corrections stacked up. Where does the name come from? Those residuals are mathematically the negative gradient of the loss. So every tree is a step downhill. But instead of stepping in weight space like a neural network, we're stepping in the space of functions, adding a whole tree each step. It's gradient descent where each step is a model. That's gradient boosting. And the trees are deliberately weak, often just stumps a few levels deep. A single one is barely better than guessing. But that's the point. Weak learners take small, safe steps so the ensemble can correct gently without overshooting. Strength comes from the sequence, not from any one tree. Because boosting relentlessly chases residuals, it can overfit. Eventually it starts fitting noise, so we control it. A small learning rate, shallow trees, and early stopping when validation error stops improving. Tune these well, and boosting sites right at the sweet spot of the bias variance curve. In practice, you don't code this from scratch. You reach for a highly optimized library, XGBoost, LightGBM, or CatBoost. They add clever speedups and regularization on top of the core idea, and they utterly dominate machine learning on structured tabular data, the default winner of data science competitions for years running. So the two great tree ensembles split the bias variance problem between them. Bagging, the random forest, trains independently to cut variance. Boosting trains sequentially to cut bias, hammering down error step by step. Forests are robust and easy. Boosting is sharper and often more accurate, but needs more care. Two paths up the same mountain. That's gradient boosting. Start weak, measure what's still wrong, and add a small tree to fix it over and over, descending the loss one model at a time. It's the quiet champion of tabular machine learning. Everything in this block so far has used labeled data. Next time, we learn without any labels at all, finding hidden groups with k-means clustering. See you there.